In this video, we'll be talking about a type of machine learning algorithm called naive Bayes. Now, neither of these words really gives us a clue as to what this algorithm is about, but going through it, we'll be able to describe why it's naive and why it makes use of Bayes' rule or Bayes' theorem. So we'll be using the same setup as we did in our decision trees video, that is, deciding whether a fish is a salmon or a tuna based on its length and its weight. So either the fish is short or long in terms of length, and it's light or heavy in terms of weight. We have a little bit of different data distribution than we did in the decision trees video, but basically the top of each cell is how many tuna are in that category. So we have 10 long and light tuna, for example, and the bottom of each cell is how many salmon we have in that category. So we have 45 long and heavy salmon, for example. Okay, so remember the goal here, as in many of our videos, is trying to decide trying to classify something based on these two observations into whether it's a salmon or a tuna. So as we see down here, given a new fish, that is given its weight, big W is kind of the random variable or denoting what's the weight. Little w is the weight itself, so that's either that's either light or heavy. And small l is the length itself, so whether it's short or long. Big L is the variable for length. So given a new fish, given its weight W and L, is it a salmon or a tuna? We want to use this data to help us make an educated decision. So at the crux of naive Bayes is calculating two probabilities, and in general, k probabilities. If you have k different classes you have, and you're trying to figure out which class an observation belongs in. In our case, we just have two classes. So we're trying to decide whether it's a salmon or a tuna. It seems natural to ask the following two questions. The first one is, what's the probability that our observation is a salmon, given it has weight W and length L? And what's the probability it's a tuna, given it has weight W and length L? If we somehow calculate these two probabilities, we can just go with the bigger one, right? Because let's say that salmon is the bigger one. So the probability it's a salmon given the weight W and length L is bigger than the probability it's a tuna given weight W and length L. So then we'll decide it's a salmon because we have more evidence, a stronger probability suggesting it's a salmon than it's a tuna. So now all it comes down to is just kind of trying to calculate these probabilities. And we'll get started in that calculation on the next page. So going forward, S is going to be salmon, just as a shorthand, and T is going to be tuna. I've tried to keep the S's orange and the T's red, but some places kind of messed up a little bit. But just keep in mind that S is salmon, T is tuna. So as stated earlier, let's try to figure out the salmon probability first. So the probability that something is a salmon, given it has weight W and length L. This is where the Bayes part of naive Bayes comes in. So I didn't write it here. Let me write it here. What is Bayes' theorem? If you remember from probability and statistics, Bayes' theorem is the probability of A given B. This is one way to formulate Bayes' theorem, the one we'll be using here. Probability of A given B is probability of A and B, and is given by this intersection symbol, A and B, close my parentheses here, divided by the probability of B. So some formulations of Bayes' theorem go further and take this numerator and cast it in terms of the opposite conditional, so probability of B given A, right? But we're going to stop here. That's all we really need, this much of Bayes' theorem. So recall that from probability. We're doing the same thing here. So probability of salmon, given this information about weight and length, is the probability of salmon and weight is the little w and length is little w, divided by the probability of B. B in this case is the conditional part of that expression. So probability that weight is equal to little w, length is equal to little l. Now, we have a fraction here, but we really only care about the numerator, and I'll explain why in a little bit. But for now, let's focus on how to calculate this probability that something is a salmon, the weight is little w, and the length is little l. So that I've rewritten right here, okay? Here we're going to kind of cast this back into the conditional, but instead of conditioning on the weight and length, we're going to condition on salmon. So we're going to flip this conditional onto the other side. So in the beginning of that process, we're going to start with putting the weight is equal to little w as our probability, conditioned on length is equal to little l, and it's a salmon. And of course, when we convert an and kind of thing, so these commas you can think of as the intersection sign if you want, same thing. So if we convert this intersection or comma and type of thing into conditional, we have to multiply by the factor that we're conditioning on. So probability that the length is little l and it's a salmon. We go one step further. We do the same calculation for that part right there. So this part remains the same as above. So this equals this. And then we condition on salmon and we have a question about what's the probability that length is equal to little l. Of course, using the same logic, we need to include this multiplier factor of the thing we're conditioning on, which is just salmon, so probability of salmon. So in all, we've casted this numerator here as the multiplication of 3 terms. Now, remember the Bayes part came into effect when we used Bayes' theorem up here. Let me write that for your reference. This is Bayes' theorem at work. The naive part comes in because we're going to be making a naive assumption. Notice here, this first term is a bit complicated, right? It's asking what's the probability that the weight is equal to little w, given the length is equal to little l and it's a salmon. The naive assumption is that all our variables, so all the explanatory variables, in this case, that's just weight and length, are independent given that we know the class of an observation. So in this case, we know the class is salmon. Remember, that's part of our conditional block here. So given that, these other variables are independent. And when we have conditional variables and independence, we can basically just ignore them when they're part of the conditional. And that's what we do down here. So following the arrow that says naive assumption, this term right here turns into probability that we have our weight as little w, given that it's a salmon. Notice this L equals little l disappeared. And an important thing to note here is it may or may not be true that they're independent. In fact, it's probably not exactly true, but it's an assumption. It's a naive assumption we make in order to help us much more easily calculate these probabilities. It might not make much sense in this case because you're saying, hey, it's such a small table, we can just look up the exact thing we want. But we'll see at the end of this video why when you have many more variables, this becomes intractable, really difficult, and we would like to make this simplifying naive assumption, okay? So in either case, we made our naive assumption, and so this multiplication of 3 terms becomes this much easier looking multiplication of 3 terms. And these we can just calculate from our table. Let's go through the first one just to kind of see what it's about. This first one is asking the question of, hey, I know it's a salmon, what's the probability that the weight is equal to little w? Another thing I did here was assign concrete values for little w and little l. So little w will be light, little l will be long, okay? So the first question is asking, if I know it's a salmon, what's the probability that it's light? I can really easily answer that question by looking at the table. If I know it's a salmon, so I only care about the salmon for this part of the question, then what's the probability that it is light? So if I look in my light row, I see there's 15 salmon here, 30 salmon here, so there's 45 salmon, and there's 100 salmon overall. So that's just 45 over 100. In the same way, the probability that the length is equal to long, given it's a salmon, is 60 over 100, using the same kind of logic. And the probability that the thing is a salmon, not conditioned on anything, is what that last term is just a half, because I have 100 salmon, 100 tuna, so 100 over 200 is a half. I multiply these factors together, and I get 27 over 200. So that means that that numerator from the very beginning is 27 over 200. Now you may be asking, what's the denominator, right? The reason we don't really care, you can calculate it, but the reason we don't really care is because, remember the other question we wanted to ask is, what's the probability that the thing is a tuna, given I have my weight w and my length l? If you were to substitute tuna for all the s's in the beginning here, the only difference you would see is that that s would be a t. The denominator would be the same. And for that reason, we don't care. Since the denominator is the same, whether this is salmon or tuna, all we really care about is which numerator is bigger. So that's why we're only considering the numerators here. Okay? So that's why the numerator in the salmon case was 27 over 200. I didn't go through all the logic, but you can go through the exact same logic flow, replace all the s's you see with t's, and refer to the appropriate values in the table. And you'll find that the probability it's a tuna, given that it's a light and long fish, is 9 over 160. It turns out that 27 over 200 is bigger than 9 over 160, so we have a higher chance, based on our naive model, that it's a salmon than it's a tuna, so we go ahead and pick salmon. We classify as it a salmon. Now, to kind of see whether this makes sense or not, let's compare that to the actual probability. So if we did not make the naive assumption, okay? And to revert back to that, we'll look at this piece of paper. So the question we asked in the beginning was, what's the probability it's a salmon given it has weight w and length l? We use Bayes' theorem right here in both cases for salmon and tuna. And we found that the exact numerator in this case, so that is, if we go through these calculations here and do not make the naive assumption, we keep this L equals L in the conditional, we find that the numerator in the salmon case is 15 over 200, and the numerator in the tuna case is 10 over 100. So compare that 15 over 100 to, I'm going to put approximation signs for what we approximated it as. We approximated this 15 over 200 as 27 over 200, so definitely off, but not too bad. And we estimated this tuna as 9 over 160. Okay, so these are our approximations, and these are the real values. It turns out that even if we use the real values, we would have picked salmon, because 15 over 200 is bigger than 10 over 200. So our approximation gives the same end result as the real values. Okay. Now, the last thing I want to talk about in the naive Bayes, so before I talk about that, that's basically what naive Bayes is. You just take your variables, you assume they're independent once you know the class of something, and you pick the probability of the class that has the most likelihood of being true given the observation you see. Now, why did we need to make the naive assumption? To really answer that, we're going to assume we have many, many more variables. So in our case, we assumed a fish only has a weight and a length, but there's many other things, right? For example, weight might not just be light or heavy. It could be many different categories, like very light, very heavy, somewhat light. And we could have other variables like color, so red or orange or some combination of those colors, something like that. So in general, let's say we have a bunch of variables, x1, x2, all the way to xn, n being potentially very large, and being able to span over many different discrete values, right? So we find that what's the probability that something is a salmon given n different values about it, right? Of course, we can start in the same way. We can apply Bayes' theorem. So let me just point out again, this is Bayes' theorem at work again. So we take the probability of the and of all of these. Notice this conditional bar just replaced by a comma, divided by the probability of the part that's being conditioned on. And of course, again, we only care about the numerator, right? So I've rewritten the numerator over here. And so this is equal to, let me just grab my last sheet of paper here. So let me maybe overlap them so you can see everything at once. This numerator is just equal to, and this is a pretty big term. So I'm going to say x1 is equal to little x1. So I'm taking this conditioned on all the other stuff inside here. So x2 is equal to x2, all the way to xn is equal to little xn, times, now I take the x2 is equal to little x2, I keep the s, I start with x3 and so on. So hopefully this conditional chain is something you've seen before. Where the last couple terms are, of course, xn is equal to little xn conditioned on salmon times probability of salmon. Okay? In other words, if you haven't seen this pi notation, it's pretty cool. It's just like the sigma, the sum notation, except you take the multiplication of everything in here. Okay? So what I should say here is that if we do not use the naive assumption, then we need to calculate all of these different things. So we need to calculate the probability that x1 is equal to little x1 given all of these different things. What's the issue with that? The issue with that is that we might not have a single example in our data set that matches everything in this conditional, because there's just so many of them, right? If n is equal to 100, I need to find an example in my data set, or a couple examples in my data set, that match exactly x2 is equal to little x2, x3 is little x3, all the way to xn is equal to little xn, and it's a salmon. I might just not have that much data, which doesn't mean that that example doesn't exist. It just means that I didn't encounter it. So that's why we use the naive assumption, because we might not have enough data samples and it might be computationally very expensive to calculate this thing. So using the naive assumption, what I basically do is say, for the first term, for example, x1 is equal to little x1. I say it's independent of everything else, given I know its class. For the next one, x2 is equal to little x2. I say it's independent of all other variables, right? Which leaves, going back to this pi notation, I jumped the gun earlier, but this pi notation, after using the naive assumption, is basically just probability of s, which I take factor out, and the probability of big xi is equal to little xi, so that's each of these guys, conditioned only on the class. And these I probably have data for, right? Because I just take all my salmon and I figure out how many fall into any one of these categories right here, okay? Whereas I might not have a data for something so specific as each of these terms that I need to multiply. That's why we use the naive assumption. It saves us some computational time. It makes sure that we have potentially some examples to draw from. And as we saw in our Little example we worked out, it's usually, I mean, it depends on the data, right? But in our case, it wasn't too far off from the truth, and it gave us the same answer as the truth would have. Okay, so that's basically naive Bayes. It's a probability-based model, which at the crux of it is Bayes' theorem, and we use a naive simplifying assumption that all our variables are independent once we know the class of a certain observation. Okay, so until next time.